A polynomial's roots are scattered across the complex plane. Draw the tightest rubber band around them. The roots of its derivative are already inside. No matter how we move the outer dots, the inner ones never cross the band. Before we explain that cage, step back to one dimension. Between any two real roots, Rolle's theorem hands us a zero of the derivative. So the derivative is trapped between the roots it came from, but our roots live in a plane. So what does the word between even mean anymore? Try the smallest case, a quadratic with two complex roots. The derivative is linear, so it has exactly 1 0, and if you compute it, you get the midpoint of the segment joining the two roots. That is Rolle's theorem, with the real line rotated into the plane. Two roots gave us a midpoint. Now add a third. The derivative is quadratic, so it has two zeros of its own, and both of them sit inside the triangle formed by the three original roots. Drag a corner wherever you like. The triangle stretches, flattens, sharpens, and the two interior dots follow every deformation but never escape. Here is the exact statement. Take any complex polynomial p with roots c1 through cn. Draw the convex hull of those roots, the smallest convex region containing them all. Every zero of p' lies inside that hull. This is the theorem of Gauss and Lucas. To see why the cage holds, rewrite the ratio p' over p as a sum. Each root contributes one simple fraction, 1 over z minus ci. Read that geometrically. Each root is a charge. Each arrow points radially away from that charge. The zeros of p' are the places where all the arrows cancel out, equilibrium. Suppose a zero of p' sat outside the convex hull. Call that candidate z. From z, look back at the roots. Each root is a positive charge, and each charge pushes z radially outward. But z is outside a convex region, so every root sits on the same side of z. Every push points into the same half of the plane, away from the hull. A sum of vectors that all tilt the same way cannot cancel. The net push on z is non-zero. There is no equilibrium out there. Every zero of p' sits inside the cage. The same theorem handles every edge case. Push all the roots onto a single line and the hull collapses to a segment. The statement becomes Rolle's theorem all over again. Place three roots at the vertices of an equilateral triangle and the two derivative roots coincide at the centroid. Every degenerate configuration respects the cage. And the statement does not flinch at scale. A polynomial of degree 50 has 49 derivative zeros, and every one of them sits somewhere inside the hull of the 50 roots. No matter how wildly the roots move, the derivative cannot invent new geography. So draw the rubber band. Every root of the derivative is already inside. The derivative cannot invent new geography.